Hello. In the last videos, we discussed many questions of disjoint union. Let's discuss the next one. Here is the question, read it and give it a try. You are given a weighted tree with n nodes and n minus 1 edges, each defined as summation f I comma j for all nodes I and j from 1 to n, which is equal to maximum value of h that is present on the simple path between I and j. Return the value of. So the question is saying that we have a tree and we have to find the maximum edge between every path. So 1 to 2, 1 to 3 and so on till every two nodes. We have to return the sum of maximum edges in that path. The constraints are n is up to 1 if I. So let's take this tree. So the value of 5 to any other node, so 5 to 4 or 5 to 1 or 5 to 2 or 5 to 3, the maximum edge is 12. So the answer is 12 into 4. And from 4, 6 is the highest with 3 nodes 1 to 3, and from 1 to 3 with weight of 2, with weight of 4, and 2 to 3 is 1. So the answer is 75. So let's assume that we have only one weight with edge, one edge with weight. Let's assume that it is E. Then what will be the answer with respect to A? It will be simply the number of nodes in this into number of nodes in this, because from this to this node it will pass through this. So with respect to single weight, the answer will be number of nodes in the left side into number of right side into that weight, because for every pair between a left vertex and right vertex it will pass through this weight. So the answer will be simply nodes left into nodes right. So now let's come to a given question. Let's think of a single edge contribution. Let's assume that we are at edge this edge and with edge weight 3, and now let's find what are the number of paths in which this can be the maximum weight possible. So let's assume that this is the edge we are thinking of, and can this edge be the part of the answer? Surely no, because we are assuming that this is the present edge and we are trying to find what are the number of paths with maximum as 3. So obviously the all edges should be of weight less than 3, but it is 4, so we cannot take any node in this subtree as well. So just disregard this. And coming to this, can we have this? Yes, because this is 2, and similarly 3, and similarly this is 3. So for this edge, what is the answer? It will be simply 1 into the number of nodes in this subtree, it is 3, and the edge weight is 3 because it is 1 into 3 into 3. Why it is 1? Because we have a weight greater than 3, so it cannot be in our path. So with respect to an edge, we can go till the edge we can find where the values are less than that. If we find an edge with greater than value, then we can just break, because it cannot be part of answer. Because if that edge is in the answer, that would be the maximum weight among the path. But we are dealing with respect to present edge weight, so obviously we can deal only with the less than weight. So from before example, we can easily see that it will be easy if at a time we are considering edge weight x. If all the weights in the tree are less than x, then it is easy to think of, because the main problem here is to find the number of nodes in the path with edge weights less than the percentage. But it will be simply O of n for every single edge, because for this we have to traverse all the nodes and we have to find the edge with values less than 3. So it will be inefficient. That's why if at a time we are trying to have all edge weights with less than the present edge weight, then we can simply use the first formula, where we can find the number of nodes in the left subtree into number of nodes in the right subtree. So if this is 4, if the value is 2 or 3 or 4, then we can say that this will be the maximum among every path between these nodes and these nodes. So how can we do this? We can simply sort the edges with respect to edge weight. So this is the first vertex, second vertex connecting the edge, and this is the edge weight. So we sorted with respect to the edge weights, and now let's start from the smallest one, so that at a present edge the weight still now are surely less than the present one, because we sorted with respect to edge weight. So coming to first one, we have 4 and 5. So let's connect this. As this is the first one, we only have 2 vertices and the answer is only 1 into 1, and the edge weight is 2, so it will be 2 with respect to this edge. And now let's come for 2 3. So for adding 2 3, we have 2 components, and now what will be the answer with respect to 3? Similarly, it will be only 3, because there is no node connected with 3 or 2 before, so it will be 3 as well. And now coming to 3 4 3, this is the first one and this is second one, and now we are trying to connect these two. And now what will be the answer? It will be 2 into 2 into 3, because there are some edges connected to 3, in the left side, and similarly there are some nodes connected to 4 in the right. So then the size is 2 because 4 and 5, and it is 2 and 3 into 3 because it's the edge vector. In this way we can try to find the answer. But how can we find the number of nodes in left or right subtree? Because for every node when we are adding, we want the number of nodes in the both subtrees. So we cannot do simply DFS or BFS. So again will be O of n. So how can I do this in O of 1? So we can simply use DSU. Because in many of the last videos we discussed where DSU is one of the best idea to think of when we are trying to get some count of nodes in a component in O of 1. So by using union by size, we can get number of nodes in a component in O of 1. So let's just sort the edges with respect to edge weight, and at an edge we can just find, for example, this is the u comma v edge and the weight is w. So what will be the answer with respect to this edge? So this is the first component, this is the second one. Let's assume this is u and this is v, and now we are connecting these two both. Because the given one is 3, so we are sure that when we are connecting an edge, there will be no path connecting between these two in the before edges, because the tree of n vertices can only have n minus 1 edges. So obviously there cannot be a cycle. So if we are trying to add an edge, we are sure that there is no path connected between u and v, so that we can simply use DSU here. So the answer will be w into size of u into size of v. And after the contribution of this edge, we will add this edge. So now we are connecting these two as well. So simply merge u and v. And we can update the sizes according to the merge function. In this way, we can simply return the answer. Let's check the code. We are inputting the values and initializing parent and size, and parent of I is equal to I and size of I is equal to 1. And we are adding the weight and the nodes corresponding to that it in the vector of pair, and we are sorting that to get according to the least weight first. And now we are traversing through all the edges and getting the node weights and node, and we are finding the parent of both nodes, and we are simply just finding size of first into size of second into the weight, and now we are simply merging those both. So simply find, we are using path compression if parent of that node is equal to itself. So we have reached, for example, this is the tree, and the parent of 0 is 0 and parent of 1 is also 0 and parent of 2 is also 0. And now for example we are trying to find parent of 2, we will return the parent of 1, and for parent of 1 we will return parent of 0, and the parent of 0 is 0 itself, so this is the ultimate parent node, so we can just simply return 0. So parent of node is equal to find the parent of node, and similarly in merge function we are trying to find parents of both, and if these both are equal they are already connected, so this is not the case here. And now if the size of u is more, so for example we have two choices, this is the first, this is the u and this is v, then it is connect to connect this one, or it is better to make this one. It is surely better to make this because we can make height balanced. So if the size of component of u is more than v, it is simply better to make parent of v is equal to u. So if size of u is greater than v, parent of v is equal to u, and we are adding, because we are adding this to this one, so the size of u will be increased and this will be the new size, which is old size of u plus new old size of v. Size of u plus size of v, and similarly the other case. In this way we can find the answer. If you have any doubts, comment below. See you in the next video.